Welcome to Brain Vision.
Okay, so we're in chapter 37, problem 60. It says, in the sun, an ionized helium atom makes a transition from n equals 5 to n equals 2 state, emitting a photon. And it says, can that photon be absorbed by hydrogen atoms present in the sun? If so, between what energy states will the hydrogen atom transition occur? Okay, so singly ionized helium is like hydrogen, except that there are two positive charges, which means Z equals 2 in the nucleus. And the square of the product of the positive and negative charges appears in the energy term for the energy levels. So we can use the results for hydrogen if we replace E squared with Z squared E squared, as we've done before probably. So that means using the Bohr model, we have En, and this equals negative Z squared now of 13.6 eV over N squared. Cool. So this is a really good way, an easy way for us to relate any hydrogen-like atom with a different nucleus, with more charges in the nucleus, for example. Okay, so for helium, we said Z equals 2 here, so let's plug that in. So we have negative 2 squared times 13.6 eV over N squared. So this is the same as negative 54.4 eV over N squared, and that's our En. Okay, so if we want the energy from N5 to N equals 2, then delta E here is just given as E5 minus E2. So this is negative 54.4 eV over 1 over 5 squared minus 1 over 2 squared. And you should see this comes out to being 11.4 eV. Okay, so if that's our energy transition, now it also asks, can that photon be absorbed by hydrogen atoms? Well, this is not the energy difference between any two specific energy levels for the hydrogen atom. You can look at that if you want to look back at the figure 26 from the previous problem. If you look from problem 56, you should see that all of the gaps between the energy levels are smaller until the very last one, or they all get bigger as you go down to lower energy levels, the gaps do, right? And the biggest the gap is, or can be, from n equals 2 to n equals 1 is roughly, what is that, 10.2 electron volts. Now, if we add another 1.9 electron volts, that gives us the n equals 3 to n equals 1 transition. Now that gets us really close, but that only gives us 11.2 electron volts. So then we go one more energy level past that, n equals 4 down to n equals 1, and that's past 11.4 electron volts. So if you look back at the energy diagram, this does not match any transition for the hydrogen series, which means this cannot be absorbed by the hydrogen atoms. So once this helium does its transition, these photons will not be absorbed by the hydrogen atoms. Cool.